Welcome to our presentation. I will talk about protecting GNSS and all about interferences today. Topics that I want to cover are as follows: defending GNSS bands, then how to test receivers, and then how to monitor interferences, and then how to report interferences, and another topic, how to analyze the performance of different GNSS satellites and report a case that we had last week in Moscow, which we reported to Russian officials. This is how it was, and this is how it still is in some receivers. Wide open floodgates. GPS and GLONASS bands are here, and the filter that is supposed to protect them, it's wide open. I was surprised to hear that a person is nominated to receive some award for saying that light squared hurts GPS signals. It's like you see it's raining outside and you want to research, go outside, see if rains fall on you. Yes, when the floodgate is open, everything will get affected. So this is what we started to work to protect GNSS bands, and in addition to prove that they work, and also to report on areas that doesn't work because people interfere within the GNSS bands. So this is what we call J-Shield, and it protects all GNSS bands. This is the actual graph from our filter on the first band. It has the slope of about 12 dB per megahertz. It covers Galileo 1, I should say it protects Galileo 1, GPS L1, and GLONASS L1. And put that in perspective, light squared 10L and light squared 10H and 10R, which were the handsets, they are fully protected. And these precious bands are free for FCC to wants to give to anybody. This is similarly for the L2 band. There are nobody is asking to broadcast anything in this band, but this is for future. We also protect similarly with about dB, 9 dB per megahertz, and we protect Galileo E5, GPS L5, GLONASS L3, GLONASS L2, and GPS L2. This was the simple part, that we have J-Shield that protects, and this is what was thought it was not possible. And if we, that are the smallest GNSS company, can do this, I'm sure the bigger one can do a lot better. Now, as I said, this was the easy part. Next is how to show, how to test and show that it works. I'm going to skip this part because I had over 100 slides presentation at the PNT conference that I showed with 4 different tests of filter characteristics. Okay, we showed by filter characteristics in-circuit tests, C over N0 test, and zero baseline test that I called it the ultimate test, that this works and has no negative effect on the performance of the GNSS system. In fact, we tested unmodified and modified, and the difference between the two were less than the zero baseline test, was less than thickness of a business card. It was about 0.2 millimeter. So I will go to other important issues that I want to talk about them for the first time. How to monitor interferences and how to report them, and the other topic of monitoring the performance of GNSS system that is our GPS system satellites. Are they performing as they should? And the specific case of Moscow that I talked about. So monitoring interferences, what we had before, things like this, like a spectrum analyzer to take to the field. It takes an expert engineer to use it, and not anybody can take this to the field. The other test setup that was done during PNT test is put things in an anechoic chamber, and we have over $1 million of equipment to test, and also it took several weeks to give the reports. What I want to present to you today, that we do better embedded in our receivers that will give you instant results, even remotely, to reporting to remote locations. We do two types of tests for monitoring inside the receiver. One is after the RF processing. We do RF analysis inside the receiver, and then is also digital analysis after digital processing is done. Now, first I talk about the RF analysis. Again, this is something inside the receiver that you push a button, spectrum, or the other one that I'll talk about later about cycloslip, and you will see all the things that I'm going to present to you today almost instantly, without needing any extra equipment or any additional knowledge than pushing this button. Now, the RF analysis section. This is the screen of RF analysis section that I want to spend a few minutes. The horizontal axis represents two things. One is in frequency domain and also in time domain. In frequency domain, each line is 10 megahertz. And the reason that they are not cascaded together is the topology of our display. You can imagine, do a Photoshop in your head and paste these three lines together horizontally. 10 megahertz, another 10 megahertz, another 10 megahertz. Each pixel represents 10 kilohertz, but shows the details of 1 kilohertz. What do I mean? There are 10 channels assigned to 10 kilohertz, each channel 1 kilohertz apart in parallel, and takes the energy. And we take the maximum energy and put it in that pixel. Although it is 1 pixel and every pixel is 10 kilohertz apart, we have the full information about the spectrum. The other information, which is in time domain, is the blue line, which is the AGC. But to put this in the scale is number 45 dB minus AGC that we read. Okay, so at any instant of time, this is the spectrum energy measurement, and at the same time is the AGC value correspondent to at the time that frequency bin was being measured. So far, this is two information: the energy and the AGC. This will take 3 seconds because we take every 10 kilohertz with 10 parallel channels every 1 millisecond. So 30 megahertz will take 3 seconds. And during this 3 seconds, we have the AGC plot. So this 3 seconds is if we take only one sample, one scan of reading. But in here, we scan 20 times and we average. So it will take, every line is not 1 second, it's 20 seconds, and the total time is 1 minute